Here's our last video on gravity. In this case, we're going to be talking about the escape velocity. With other words, when a rocket takes off from the Earth, how fast must it be going so that gravity will not slow down to the point where it will eventually stop and return back to Earth. So it has to have enough velocity, so even though it goes farther and farther away from the Earth and kinetic energy is being converted to potential energy, it will always have some kinetic energy left to keep going and never stop. Or in the limit, when it finally reaches the infinite distance away from the Earth, at that point it can stop. At that point it will no longer fall back to the Earth because it's so far away from the Earth that gravity will no longer pull it back. So how do we find that escape velocity? The way you do that is using the energy equation, that the kinetic energy initial plus the potential energy initial equals the kinetic energy final plus the potential energy final. So since we're looking for the very minimum velocity required to escape, the escape velocity, we can say by the time it reaches an infinite distance, all the kinetic energy will have gone to zero. And of course, by definition, when your distance is at infinity, potential energy at that point is also equal to zero. So what we then have to say is that the kinetic energy initial plus the potential energy initial equals zero. Of course, the kinetic energy initial will have to be 1/2 mv squared. And of course, the velocity required is the escape velocity, so we'll write v sub e. And the potential energy initial will be the potential energy it has at the Earth's surface. So it would be minus, I keep forgetting my g, so minus gm big M over r. That, of course, would be the radius of the Earth. And that has to equal 0. So now we're going to solve this equation for velocity escape. So first of all, you can see that the mass doesn't matter. That cancels out from both sides. Then we have 1/2 the escape velocity squared is equal to bringing this to the other side. It becomes positive. It's gm divided by the radius of the Earth. Then we multiply both sides by 2, so we get v initial squared is equal to 2 times gm over the radius of the Earth. And finally, when we take the square root of both sides, we can see that and it should not be v sub naught, it should be v sub e, because we're looking for the escape velocity. So we see that escape velocity is equal to the square root of 2gm over the radius of the Earth. All right, now, I noticed something here. Let me rewrite this and maybe you see it as well. So if I now take the escape velocity is equal, this pen is indeed better, I'll write as the square root of 2 times the square root of gm over the radius of the Earth. Notice this quantity right here. What does it remind you of? That is actually the orbital velocity equation. So we can say that the escape velocity is equal to the square root of 2 times the orbital velocity of the Earth. And so that can now simply be an equation like that, where the escape velocity is simply about 1.4 times the orbital velocity. And if you remember what the orbital velocity was for the Earth, which was around 7,900 meters per second, so the escape velocity is equal to the square root of 2 times about 7,900 meters per second. And let's see what that is equal to. So 2, take the square root, times 7,900, and that would be about 11,172. So it would be about 11,170 meters per second. If you convert that to miles per second, so divided by 1.609 equals, and that's roughly about 7 miles per second. All right, so now you can see how we calculated escape velocity. We assume that at the very end, there would be no kinetic energy left, and of course we will reach infinite distance, meaning potential energy is 0. That means we set the initial kinetic energy equal to the final potential energy, and that means the escape velocity is the square root of 2 times the orbital velocity, about 7 miles per second for the Earth. By the way, if you want to get away from the sun, if you leave the surface of the sun, you would need a speed of about 642 miles per second. So you see, the bigger the object, the greater the escape velocity needs to be. But here's a good example of how to calculate that.